Hi everyone, this is Vasvi from Atom Tuition. Today I will be, the topic of mathematical induction is found to be very difficult to a lot of students. It is not really that hard and we don't use it in our day-to-day life too, but still it is purely a mathematical process. Let me explain you the term induction and deduction. Normally what we do is, in deduction, we use these two tools in math. We do deduction as well as induction. So in deduction what we do is, we take a general formal rule which has already been established and we apply for specific cases and we get the results. Okay, in deduction that was we do the general accepted formula from we use a general accepted formula for the specified cases, we arrive at the result. Okay, in induction it is just the opposite. We just take few specific instances and then from that we generalize it. Okay, we generalize a formula or something. So this process of taking specific instances and generalizing it is called induction. So this is what we are doing here. And one more thing I would like to say is, mathematical induction is a formal proof. Okay, it is a formal proof. Therefore, the steps are to be strictly followed. It has got only very few steps. Okay, and it's a theoretical portion. So what is important is, you have to repeat certain statement for every problem to arrive at the answer, and that's what earns you marks. Okay, now let me explain what the mathematical induction by definition is. Suppose there are a given statement P of n, okay, involving the natural number n, where n is a natural number, such that what we first do is, we say the statement is true for all n equals 1. Okay, when you substitute n as 1, the given statement should be true, and then we assume that it is true for n equals k. Okay, here we are doing the assumption. Secondly, we do the assumption that the statement is true for all n equals k, where k is some positive integer. Okay, fine. If it is so, if n equals k is true, then we also conclude that the statement is true for all n equals k plus 1. Okay, and thereby it is true for all natural numbers. So this is what we do. So this is the same repeated process we do for each and every problem, and it's nothing hard if you really understand it. So I can explain you how to solve these type of problems with few examples. Here I have taken, prove the following by using the principle of mathematical induction for all n belongs to n. Okay, that's a natural number. So this is the statement given. They say 1 cube plus 2 cube plus 3 cube plus n cube. Okay, where it goes on till n number of terms, and n cube will be equal to n times n plus 1 over 2, the whole square. Okay, so here this n cube is nothing but the last term of the series. We have each series here, right? Likewise, the last term of the series is n cube. So let us do like what we have said before. First we have to say that the statement is true for n equals 1, right? So let us take P of, this is P of 1, P of n, right? So what will the P of 1 be? It is just 1 cube, right? You just have one term, so that's 1 cube, and this side you have 1 times 1 plus 1, your n is 1 here, over 2 the whole square, right? So that implies you have 1 here on your left hand side, and on your right it is 1 plus 1 is 2. 2 over 2 squared is equal to 1, right? So it is true. Therefore, P of 1 is true. Okay? Now we assume, remember we use the word assume. So what we say is, let P of K be equal to, right? So here P of K should be equal to, here instead of N we have K, right? So it would be like K times K plus 1 the whole divided by 2 whole square. Okay? So this is true. Let us take this as true. Okay? Then, now what we do is we are going to find P of K plus 1. Okay? So actually P of K plus 1, what will it be? I'll write that in the rough column. In the place of N, if you are substituting K plus 1, what should you get? It would be like N into N plus 1, right? So N here is K plus 1 times N plus 1. So that is K plus 1, right? So that would be K plus 2 over 2 the whole square. So this should be this. Let us see if it is true. So here P K plus 1 will be equal to, it is like 1 cube plus 2 cube. Okay, I write the series again. 3 cube. So on it goes. And you have plus K cube, right? Plus K plus 1 the whole cube, right? Because you have one more term here. Now you know that this would be, this is equal to, here we have already proved it, for K terms, P of K, right? P of K is going to be K times K plus 1 whole thing divided by 2 whole squared plus K plus 1 the whole cube, right? So in the next step what I do is, it would be like, I'm just giving the square inside. So it is K square times K plus 1 the whole square over 2 square. I keep it as 2 square plus K plus 1 the whole cube. Here I can take the K plus 1 the whole square out, right? As common. So that implies, so this would be like, you take the whole square here, 2 square, and here when you take the K plus 1 the whole square out, what happens? You are left with K square plus, here you will have 2 squared times K plus 1, right? Because it didn't have the denominator, so we have taken it. Okay. Now this I'm going to solve. So this would be like K plus 1 the whole square times K square. When you multiply the 2 square inside, it is plus 4K plus 1 whole divided by 2 square, which implies K plus 1, and this part is K plus, oh this is 4, sorry, this is K plus 2. You have all squares, I'm going to put that in common, to the whole square, right? Is true. Now this is also true. You have proved that it is true. So you have to write this last statement here. Therefore, P of N is true for, equivalent to, for all N equal to natural numbers by mathematical induction. Okay, by mathematical induction. Yeah, you have to write this statement after every problem. Okay, so that is solved. I hope you understood this. So I have taken another question. This is different type. Here they say 5 raised to 2n minus 1 is divisible by 24 for, you need to prove this, for all n is a natural number. Okay, what we do is we have p of n now as p of n equals 5 2 raised to n minus 1, right? So what will p of 1 be? P of 1 is equal to 5 times 2. They say this is divisible by 24, right? So here this would be 2 times 1 is 2 minus 1, which is 25 minus 1, right? Is 24. Definitely divisible by 24, right? So is true. Next we take p of k, okay? We assume if p of k equals 5 raised to 2k minus 1 is true, then we'll come to that later. We need to prove p of k plus 1 now, right? K plus 1 is equal to 5 raised to 2 times k plus 1, okay? The place of n I put k plus 1 minus 1, which is nothing but 5 raised to 2k plus 2 minus 1, which is equal to 5 squared times 5 raised to 2k minus 1. Okay, this 5 raised to 2k I just give you here. 5 raised to 2k minus 1, we know it is divisible by 24, right? So I just take it is 20, it is something like 24c, where c is a constant. Okay, it is 24c, so I am just going to substitute that here. So here 5 raised to 2k would be equal to 24c plus 1, right? Okay, now here let me apply that. This is 25, right? This is 25 times this is 1, 2, 25, 2 raised to k, we have got this. This I would write as 24c plus 1 and minus 1 here. So this would be like 24c times 25, distributive law, plus 25 minus 1. So this shows that it is 24c times 25 plus here too it is 24. So that implies the whole term is divisible by 24. Okay. So again you have to write the last statement, don't forget. Hence by mathematical induction it is true for all n belongs to natural number. So I repeat once again, all we are doing is first we substitute that p of 1 in the initial process is true. Okay, so for the initial process you take it as p of 1 and you show that it is true. Then you assume that p of k is also true. In that case p of k plus 1 should be true. We have to prove on that, and if all these are proved, then you can conclude that it is true for all natural number by mathematical induction. Okay, hope you all would have understood what has been said here. Thank you. Bye.